It is just past midnight in a satellite control room on a chilly December day in 2025. The room is quiet, bathed in the soft blue glow of a dozen monitors. Outside, the world sleeps, but in here, a team of engineers keeps a vigilant watch over $1 billion piece of technology, orbiting 500 kilometers above the Earth. Suddenly, a series of red alerts cascade across a primary screen. An alarm, soft but insistent, breaks the silence. The satellite, a vital link in our global communications network, has just reported a string of incomprehensible data glitches. Its internal temperature sensors are spiking without reason, and its memory banks are showing signs of corruption, as if a cosmic ray just punched through its digital brain. The lead engineer, a woman with 2 decades of experience, doesn't panic. She knows exactly what is happening. She brings up a map of the Earth on her display, tracking the satellite's orbital path. A glowing red oval highlights a vast area stretching from the coast of Brazil to the southern tip of Africa. "It's in the anomaly," she announces to the room, her voice calm and steady. "Begin safe mode sequence. Power down the primary science instruments. We'll ride it out." This scene, or one very much like it, plays out more and more often in control rooms around the world. It is a direct and tangible consequence of a silent, invisible change happening to our planet. The problem is not with the satellite itself. The machine is performing as designed. The problem is with the space it is flying through. Earth is protected by an invisible shield, a magnetic field that deflects harmful radiation from the sun and deep space. But that shield is not perfect. In certain places, it is growing weaker, thinner, and less reliable. The satellite had just flown through the largest and most troublesome of these weak spots, a region known to scientists as the South Atlantic Anomaly. Here, the planet's natural defenses are at their lowest, and the torrent of charged particles from space can penetrate deeper into our atmosphere, right into the path of our orbiting technology. For the team in the control room, this is now a routine hazard. They know the drill. They will wait for the satellite to pass through this dangerous zone, a journey that takes about 20 minutes. Once it emerges on the other side, they will carefully bring its systems back online, assess any damage, and hope for the best. Most of the time, the satellite recovers with just a few scrambled bits of data. But with each passing year, the anomaly grows larger and weaker, and the risk of a catastrophic failure increases. This is the front line of a global challenge, where our high-tech world collides with the slow, powerful forces of our own planet. To understand what is happening to our satellites, we first need to understand the incredible force that protects them and us. Imagine Earth not just as a solid ball of rock, but as a giant spinning magnet. Deep beneath our feet, thousands of kilometers down, is the planet's outer core. This is a massive ocean of liquid iron, hotter than the surface of the sun, churning and flowing in massive, slow-moving currents. This constant motion of molten metal acts like a colossal dynamo, generating a powerful magnetic field that surrounds our entire planet. It is a process called the geodynamo, and it is the reason a simple compass needle points north. This magnetic field is not something you can see or feel, but it is one of the most important features of our world. It extends tens of thousands of kilometers out into space, forming a protective bubble called the magnetosphere. Think of it as Earth's very own force field. When the sun unleashes a powerful solar flare or a stream of charged particles known as the solar wind, this field stands in the way. It deflects most of the harmful radiation, guiding it safely around our planet. Without this shield, Earth's surface would be bombarded by deadly cosmic rays, and our atmosphere would have been slowly stripped away into space millions of years ago. The magnetic field is the unsung hero of life on Earth. It is what allowed life to emerge from the oceans and thrive on land, safe from the harsh radiation of space. It is what creates the spectacular northern and southern lights, the auroras, where particles from the sun are channeled down into the atmosphere near the poles, lighting up the night sky. For centuries, humans have used this field for navigation, guiding ships across vast oceans and explorers across uncharted continents. It is a constant, reliable presence, a fundamental part of the planetary system that makes our world a habitable oasis in the cold emptiness of space. But this field is not static. It is not a permanent fixture, like a mountain or an ocean. Because it is generated by the dynamic, ever-changing flow of liquid iron in the core, the magnetic field itself is also in a constant state of flux. It strengthens and weakens. It shifts and wanders. The magnetic North Pole, for instance, is not fixed at the geographic North Pole. It drifts, and in recent decades, its pace has quickened dramatically. These changes are a natural part of our planet's life cycle, but today, with our civilization so dependent on technology, we are watching them more closely than ever before. For a long time, we thought of the magnetic field as a mostly stable shield. We knew it changed over geological time, even flipping its poles every few 100,000 years. But new data, collected by a trio of European Space Agency satellites called SWARM, has given us an unprecedentedly detailed look at our planet's magnetic heartbeat. What we are seeing is surprising and, for some, a little concerning. The field is not just changing. In some areas, it is changing at a rate up to 10 times faster than many of our older models predicted. The global strength of the field has weakened by about 9% since the 1800s. This weakening is not happening evenly across the globe. It is a patchy and complex process. While some areas, like the region over Siberia, have actually seen their magnetic field strength increase slightly, other areas are experiencing a much more rapid decline. The biggest area of concern is a vast and growing dent in our magnetic shield, known as the South Atlantic Anomaly. This is a huge region stretching from South America across the Atlantic Ocean towards Africa, where the magnetic field is significantly weaker than anywhere else on Earth. It is as if our planet's protective armor has been thinned out over a massive area. The SWARM satellites have shown us that this weak spot is not only getting weaker, but it is also expanding. Since 2014, the area of the anomaly has grown by a size nearly equivalent to half of continental Europe. Its weakest point has dipped even lower, offering less and less protection from incoming radiation. Furthermore, the anomaly appears to be splitting into two separate lobes, or centers of weakness. A second weak patch has emerged southwest of Africa and is intensifying at an alarming rate. This suggests that complex and turbulent processes are happening deep within the Earth's core, right beneath that region. Scientists believe these weak spots are linked to features called reverse flux patches at the boundary between the core and the mantle. These are strange areas where the direction of the magnetic field is flipped, flowing back into the core instead of out of it. These patches seem to be destabilizing the field from below, causing the overlying shield to thin out. While this does not mean the world is in imminent danger and a full pole reversal is about to happen tomorrow, it does mean that the space environment directly above this region is becoming increasingly hazardous for the technology we rely on every single day. For a satellite orbiting the Earth, flying through the South Atlantic Anomaly is like flying through a storm of invisible bullets. In most parts of its orbit, a satellite is safely cocooned within the strongest parts of the magnetosphere, which deflects the vast majority of high-energy particles from the Sun and from distant cosmic events. But when its path takes it through the SAA, that protection suddenly drops. The field here is so weak that the inner Van Allen radiation belt, a zone of trapped energetic particles, dips down to just a few hundred kilometers above the surface, right into the flight paths of many low Earth orbit satellites. This sudden exposure to intense radiation can wreak havoc on a satellite's sensitive electronics. High-energy protons can slam into microchips, causing what engineers call a single-event upset. This can be as simple as flipping a single bit in the satellite's memory from a 0 to a 1, leading to corrupted data or a faulty command. In more serious cases, these particles can cause a short circuit, permanently frying a critical component and rendering a multi-million-dollar piece of equipment useless. It is the electronic equivalent of a sudden, debilitating illness, and it happens without any warning. The consequences are very real. The Hubble Space Telescope, one of humanity's greatest scientific instruments, has to suspend its observations every time it passes through the anomaly. Its sensitive cameras and detectors are simply too vulnerable to the radiation, which creates snow and false signals in its images. Mission controllers for countless other satellites, from weather monitors to communications relays, follow similar procedures. They put their spacecraft into a protective safe mode, temporarily shutting down non-essential systems to minimize the risk of damage. It is a necessary precaution, but it means valuable operational time is lost with every single orbit. The problem is growing. As the SAA expands and weakens, more satellites are affected for longer periods of time. This is especially true for the new mega constellations being launched by companies like SpaceX and OneWeb. These networks consist of thousands of smaller, often less protected satellites blanketing the globe to provide internet service. A larger and more intense anomaly means a greater statistical probability of failures across these vast fleets, which could disrupt the very services they are designed to provide. For satellite operators, the SAA is no longer just a known hazard, it is a growing operational nightmare. It is not just robotic hardware that is at risk in this hostile region of space, humans are too. The International Space Station, our home in orbit, also passes through the South Atlantic anomaly several times a day. While the station's hull provides a significant amount of shielding, it cannot block everything. When the ISS traverses the SAA, the astronauts on board are exposed to a higher dose of radiation than at any other point in their orbit. For me and my fellow astronauts, this was a known and carefully managed part of life in space, a reminder that we were living just on the edge of Earth's protective bubble. The effects of this radiation on the human body are a serious concern for space agencies like NASA and the ESA. These high-energy particles can pass through living tissue, damaging DNA, and increasing the long-term risk of health problems, including cancer and cataracts. Astronauts wear dosimeters, small devices that constantly measure their personal radiation exposure. These readings are monitored closely by flight surgeons on the ground. Mission planners try to schedule spacewalks or extravehicular activities to avoid passing through the SAA, since an astronaut's spacesuit offers much less protection than the heavily shielded walls of the station. Inside the station, the effects of the anomaly are sometimes surprisingly visible. Astronauts have reported seeing strange flashes of light in their eyes, even when they are closed. These are thought to be caused by high-energy cosmic rays striking the optic nerve or the visual cortex of the brain. It is a direct personal experience of the invisible radiation storm raging just outside the window. Laptops and other sensitive electronic devices used on the station are also prone to crashing or glitching more frequently when the ISS is flying through this region, mirroring the problems faced by unmanned satellites on a much more personal level. As humanity plans for longer missions, including returning to the Moon and eventually traveling to Mars, understanding and mitigating the effects of space radiation becomes even more critical. The journey beyond low Earth orbit will take astronauts outside the protection of the magnetosphere entirely, exposing them to the full force of solar and cosmic radiation. The South Atlantic anomaly serves as a valuable, if challenging, natural laboratory. Studying how the field's weakness affects our technology and our bodies in near-Earth orbit helps us prepare for the much greater hazards of deep space exploration. The lessons we learn there are essential for our future as a spacefaring species. Faced with this growing environmental challenge, engineers and space agencies are not standing still. They are actively developing new strategies and technologies to protect our vital assets in orbit. The first line of defense is to make the satellites tougher. This approach is known as radiation hardening. It involves designing and building electronic components, such as processors and memory chips, that are inherently more resistant to the effects of high-energy particles. These hardened components are made with different materials and manufacturing processes, making them less likely to fail when struck by radiation. Another key strategy is adding more shielding. This can be as simple as placing a satellite's most sensitive electronics deep within its structure, using the rest of the spacecraft's body as a physical barrier. In some cases, layers of dense materials like aluminum or tantalum are used to encase critical systems, acting like a suit of armor against the invisible onslaught of particles. However, shielding adds weight, and weight is the most expensive commodity in the space business. Every extra kilogram of shielding costs thousands of dollars to launch, so engineers must perform a careful balancing act between protection and cost effectiveness. Beyond building tougher hardware, operators are also getting smarter about how they fly their spacecraft. Mission planning now explicitly accounts for the South Atlantic anomaly. Satellite orbits are sometimes designed to minimize the time spent within the weakest parts of the field. As we saw in the control room, operators can proactively power down non-essential or particularly vulnerable systems just before a satellite enters the SAA and power them back up once it is safely through. This operational dance reduces the wear and tear on the electronics and extends the functional lifespan of the satellite. Redundancy is another crucial element of modern satellite design. For critical systems, engineers often build in backups. If a primary processor is knocked out by a radiation hit, a secondary processor can take over automatically. This fault-tolerant design ensures that a single event upset does not lead to the complete loss of the mission. By combining these approaches, stronger components, better shielding, smarter operations, and redundant systems, the space industry is adapting to the changing reality of our planet's magnetic field, building a more resilient fleet to navigate the increasingly challenging environment of low Earth orbit. Reacting to the South Atlantic anomaly by shutting down instruments is effective, but it is not ideal. It is a defensive maneuver. The ultimate goal for scientists and satellite operators is to move from reaction to prediction. Just as meteorologists forecast hurricanes on Earth to give communities time to prepare, space weather scientists are working to develop reliable forecasts for the magnetic field and the radiation environment. This would allow satellite operators to anticipate high-risk periods with greater precision, optimizing operations and taking preventative action before a problem occurs, not after. The foundation of any good forecast is good data. The ESA's SWARM mission has been a game changer, providing continuous, high-resolution measurements of the magnetic field from space since 2013. This decade-plus of data allows scientists to track changes with incredible accuracy, identifying trends like the growth of the SAA and the rapid drift of the magnetic North Pole. To complement this view from above, a denser network of ground-based observatories is also needed. These ground stations provide a constant baseline measurement, helping to calibrate the satellite data and build more comprehensive models of the Earth's core dynamics. The next step is to turn this data into predictive models. This is an immense computational challenge. Scientists are using supercomputers to simulate the complex fluid dynamics of the liquid iron in Earth's outer core. By feeding these models with real-time data from SWARM and ground observatories, they hope to create a system that can forecast how the magnetic field will evolve over the coming months and years. This is not just about tracking the SAA. It is also about predicting the behavior of the entire magnetosphere, including its response to major events on the Sun, like solar flares and coronal mass ejections. A successful space weather forecasting system would be invaluable. It could provide satellite operators with a 5-day forecast of radiation risk, much like a standard weather report. It could warn of periods when the SAA is expected to be particularly intense, or when a solar storm is likely to compress the magnetosphere, increasing radiation levels globally. This would enable more efficient mission planning, reduce the risk of satellite damage, and enhance the safety of astronauts. We are not there yet, but the progress is rapid. We are learning to read the subtle signals from deep within our planet to better protect our technological civilization on its surface. While the most dramatic effects of the weakening magnetic field are felt in space, there are important ripple effects that reach all the way down to the ground. Our modern world is deeply interconnected with the infrastructure we have placed in orbit. When satellites are at risk, so are the services we rely on every day. Consider the Global Positioning System, or GPS. This network of satellites provides precise timing and location data, not just for the navigation app on your phone, but for everything from global financial transactions and agricultural machinery to emergency services and shipping logistics. During intense geomagnetic storms, which are made worse by a weaker global shield, the accuracy of GPS can be degraded. The charged particles in the atmosphere can delay and distort the signals traveling from the satellites to your receiver on the ground, introducing errors of several meters. For most of us, this is a minor inconvenience, but for an airplane on final approach to a runway in poor visibility, or for an automated farming tractor planting seeds with centimeter-level precision, these errors can have serious consequences. The rapid drift of the magnetic North Pole also forces more frequent updates to the navigation models used by aviation and maritime industries to ensure their compasses remain accurate. High-altitude flights, particularly those that travel over the polar regions, are another area of concern. These routes are popular because they are the shortest distance between continents, but they fly through areas where Earth's magnetic field lines dip down into the atmosphere, offering less protection from solar and cosmic radiation. Airlines and aviation authorities closely monitor space weather to manage radiation exposure for both crew and passengers on these polar routes. If a major solar storm is predicted, flights may be rerouted to lower latitudes, adding time and fuel costs to the journey. A persistently weaker global field could make such events more common. Finally, our terrestrial power grids are also vulnerable. A major solar storm can induce powerful electrical currents in long transmission lines on the ground, a phenomenon known as geomagnetically induced currents, or GICs. A weaker magnetic shield means that a more powerful surge of energy can reach the ground during a storm. These currents can overload and damage high-voltage transformers, the backbone of any power grid, potentially leading to widespread and long-lasting blackouts. Power grid operators are increasingly incorporating space weather forecasts into their operations to prepare for these cosmic threats, highlighting how our planet's magnetic health is directly linked to our own energy security. The quiet drama unfolding in the South Atlantic anomaly is more than just a technical problem for satellite engineers. It is a profound reminder of our intricate connection to the planet we call home. We have built a dazzling technological civilization that reaches into space. But all of it, every satellite, every GPS signal, every astronaut, operates within a physical environment governed by immense natural forces. We live and work under the protection of an invisible shield forged in the heart of our world, and now we are watching that shield change in real time on a human timescale of years and decades. It is important to keep this in perspective. The weakening of the magnetic field does not pose any direct danger to life on the surface. Our thick atmosphere provides an excellent and primary shield against harmful radiation, and it is not going anywhere. The changes we are observing do not signal an impending apocalypse or a catastrophic pole reversal that will happen overnight. These geological processes unfold over thousands of years. What we are witnessing is a restless phase, a period of rapid fluctuation in a system that is constantly in motion. It is a scientific marvel, an opportunity to learn more about the deep inner workings of our planet. This evolving situation underscores our dependence on a stable planetary environment. For most of human history, the magnetic field was simply a given, a reliable tool for navigation. Today, it is a critical variable in the equation of our global infrastructure. Its fluctuations affect our communications, our economy, our security, and our ambitions to explore the cosmos. Understanding these changes is not just an academic exercise, it is a practical necessity. It drives us to innovate, to build more resilient technology, and to develop the foresight needed to navigate the challenges ahead. Ultimately, the story of the weakening magnetic field is a story of awareness. It reminds us that we are not separate from nature, but an integral part of it. The same planet that provides us with air to breathe and water to drink also generates a dynamic shield that protects our way of life. By watching it change, we learn more about our world and our place within it. We are like sailors who have finally learned to read the subtle shifts in the wind and the currents, not with fear, but with respect and a growing understanding. And with that understanding comes the wisdom to prepare, to adapt, and to continue our journey forward.